Hi folks, aluminum. We always cut 60/61, but there's also 20/24 and 70/75, and there's probably even more. But let's do a test. Let's take this chunk of 20/24, this chunk of 60/61, and that chunk of 70/75, and let's turn it and let's look at understanding chip formation and lathe inserts and the nose radius and the surface feet and how to understand how to set up a new recipe. Let's hit the road though. Remember the grinding video? We're back. It's Mr. D-Bolt. Let's learn from the experts. Paul saw our video like a year or two ago when we were really struggling with chip breaking. It was actually, I think, a larger steel piece. And so we've been talking for months now about setting up a lathe, reading a tool, reading chips, and he keeps mentioning 20/24 aluminum and then 70/75. And I've never cut these because I just feel like we live in this world where everyone uses 60/61 for I have no idea even why. So we've got the three pieces. Shout out to Alro. Alro actually hooked us up with these drops, which is pretty awesome. We're saw cutting the piece of 70/75 now. Here's the tool I brought. What do you think when you see that?
When you look at these tools, you see how it's got a coating on there. It makes it real shiny, which makes it really slippery, which is, if you've cut much aluminum, you know right away it wants to stick. So that's why it's coated like that. And then you got a real high chip breaker on there where it's really sharp on the edge, which makes it want to shear. And that
also good for aluminum.
Yeah, that's right. Makes it work for aluminum. You notice the clamping system is different than this holder would be for steel, mainly because it doesn't have to take as much force as a steel engine.
So the screw is weaker than having that overarm bar.
That's right. That's right. That's why it's made that way. And then you notice this one doesn't have a seat in it.
Yep.
So it's less likely to fracture than a steel one.
Okay. Now that, I would assume that, is that a positive, you know, it's almost like it's a positive insert in a neutral or negative holder?
Yeah, well, it's a positive. If you look at the sides of it, this is a positive insert.
Okay.
Because it's straight inside here. It's not at an angle.
Okay.
Now, you know, you can say, well, I'm not going to get as many cutting edges this way because I can't flip the insert over.
Yep.
And
right.
You know, that's a sacrifice you make with a positive insert.
Yep.
You just can't.
We'll only get two here in this holder, although Brian Block, who has a great YouTube channel, showed me you can buy another type of holder that makes use of the other two edges, but there's still only going to be 4 edges on that tool max.
What's the advantage of that? You know, why there is an advantage to having the other holder.
What? Well, you get used.
It takes less horsepower.
Why is that?
Because it spreads the chip out.
Huh. Interesting. Well, that's usually too. And I know Paul has a little bit of a bigger machine here, but I don't want you guys to be intimidated. What I hope the takeaway today is reading the chips, whether you've got a Sureline or whether you've got a huge Monarch, understanding, setting up this tool and kind of reading the chips.
Yeah. So we'll set it up here and get it on center and everything when we'll get a piece set up here. We'll talk about the machine a little bit and setting the tools and probably going to indicate the face here because we want to present the tool at the right angle. If you put it in a CNC machine, you'll notice you want to keep everything clean and keep everything square.
Right.
And this is designed to cut that way. If you put it at angles like that, it will cut, but it won't be as efficient as it would be the way it's designed.
Huh.
So, you know, when I set up a machine, I'll indicate one holder. All my tools are indicated on one side, so they're all perpendicular. So if you're going to do a groove or you're going to turn or anything, all the angles are correct on the front tool.
So you never adjust the top post on your Aluris?
Oh yeah, you can't. You can't get away from it.
But that's going to throw out your line.
Ideally, you don't want to. Right. You don't have to.
Okay.
Because mainly the insert tools are not designed for that.
Really?
They're designed to put in a CNC machine and cut straight all the time.
Interesting. Huh.
So, you know, the other thing is, if you're doing a groove, boy, if it's not indicated, you've got problems all over the place. You know, you're putting a bind on it. It wants to groove crooked and everything because it's not straight. And you want to put that stress on it exactly as even as you can to get it to cut nice. And that's true of your threading inserts too. You want them to be lined up so they thread correctly.
It's funny because threading, I think about doing that because you want good threads, but something like grooving, like stack the deck in your favor. You're making a more accurate part, lower tool pressure, better performance out of the machine. If you have a problem, you know it's something else maybe and not your setup.
Yeah. This particular machine is a 2060.
2060, 20-inch swing. Okay.
60 inches between center. It's a real common size. The reason we have this size in here, it has a real good blend of horsepower, rigidity, and speed. You need speed for surface footage to get the right surface footage on your parts.
Yep.
You need horsepower. This particular machine's a 10 horse.
Yep.
Okay. And it's got rigidity. You'll find that if you go out in the industry, this is the most common size because it has that blend of those three elements.
Paul's not kidding too. Look at these chunks of 4140 that he got in for a job, which he's putting on hold to let us film this morning, which we very much appreciate. But you're not messing around.
Yeah. So this way you can take advantage of these cutting tools. A lot of people, they get smaller machines and they don't adapt to carbide very well at all because they don't have the rigidity or the horsepower. And the efficiency of it's not that you can't use carbide. The efficiency goes way down when you don't have any horsepower or the machine's not very rigid.
And that carbide's expensive.
That's right, you know, and you can say, well, I'm using carbide because I don't want to have to grind cutting tools all the time. Well, certainly that is the big advantage. You can buy the shapes ready-made, but everybody knows that carbide tools are not cheap. But
do you use any high-speed steel?
As little as I can get away with.
Yeah, okay, so no.
Yeah. Well, you know, sometimes you get backed into a corner. I have a tool and cutter grinder back here. I can grind my own tools, but it takes too much time to grind tools. If you find that you buy inserts, they're cheaper than grinding tools. It's hard to get the tools ground really nicely, especially if you're doing more than multiple parts or you've got an odd shape or something. It's really easy to buy a tool.
Yeah.
Whereas if you're grinding it, you got to have certain skill sets to do that too. It's just like anything else. It's a specialty in itself. And to get a real nice job, you have to know what you're doing. You have to have a machine. Well, if you're doing it on a pedestal grinder, boy, it's burning burning the tool and all that. If you can buy it, it's easy to buy it. Now, I'm not saying. I mean, I've got a threading insert here.
Yeah.
This Acme threading insert right here.
That's crazy. Look at this.
Yeah.
Holy cow. That is a monster. This frac. Okay,
yeah. That one's been used.
Yeah, right.
Those inserts are $50 a piece.
Wow. And you only get two cutting edges.
Two cutting edges, $50 a piece. So inserts can be very expensive.
Yeah.
Depending on what their purpose is, but you know, it's not that you don't use high speed. It's just that it's like an emergency setup. I can't do anything else right now. Somebody comes in, wants something right now. I don't have a tool. Let's grind it, get it done.
Right.
If you can buy it, it comes in tomorrow. You might say, well, maybe I'm going to wait and buy one because it's going to be very effective. And, you know, we're talking about engineering at these tooling companies. They've got all that backup. They've got all these people that study this all the time, and they're going to get a real effective use out of your tool.
And you know, we've started buying a lot of our tooling from Sandvik, and it actually is maybe the more expensive option, but I've gotten to know Corey, the rep.
Yeah.
And here's the thing, they kind of take on that responsibility of helping you with fees and fees, and they will do this for even small shops. I don't buy that. I probably buy a few grand or a year of tools, maybe not even. And before we were that high, they were still helping us, and they'd say, hey, try WNMG, here's your starting feed rate. They'll kind of help you out, and that's huge for small guys.
Yeah, you know, and it's a matter of what John's talking about is support, you know. Will they help you?
Yeah.
In my mind, they're well worth it because the most valuable thing you have in your shop is time.
Yeah.
And these tools are way faster than any high-speed tool ever thought of being.
Right. And as expensive as some of these inserts are for me, tooling cost is such a small percent. I'm not in a production environment.
Yeah.
It's such a small cost of my overall year that I don't really care anymore. If I spend a little bit extra, like I used to be a bootstrapper. I used to go frugal. I used to try to find used on eBay or whatever. And I just like, you know what? There's actually a pretty big fraud market of used inserts that are mismarked.
A lot of them have been, you know, they'll have a brand name on there and they've been made in China and they just put it in a brand name box.
Yeah.
So you got to be very careful about buying things on the internet. You say, well, I bought Sandvik inserts on the internet and they're no good because somebody put Chinese inserts in that Sandvik box and told you they were Sandvik. You know, I mean, if you've worked at some big corporations, a lot of those companies they'll have a department called statistical process control, and they'll go out and study these inserts, and they'll understand what the best inserts are. And believe me, it's not these fly-by-night companies. It's these guys that are been working at it, engineered it, and everything else. So we'll let's talk about the insert and the setup a little bit. You got to have a rigid machine. Now this is a 2060, like I said earlier. You don't need a 2060. I have another machine in the other room here. It's a 1440. Me personally, that's about the smallest machine I would get.
1440, okay.
They're stiff and they got some horsepower, and you can get some with a little more speed.
We'll go look at it in a minute. It's not a huge machine. You've got that in your garage.
No, you know, and I realize it's not one you would carry down the staircase in a house either. But you know, if you're wanting to machine with some proficiency, you're not going to do it with much smaller than that.
Fair enough.
You know, and I mean, it's a 5-horse machine, which is pretty good horsepower for.
Yeah, that is a lot. Right.
But it's still. If you want to use carbide and you say, well, I can use high speed, you can. How valuable is your time? If you're a young guy, maybe you got more time than an older guy. I'm on the other end of the spectrum. I'm trying to get the most done that I can as fast as I can. And if you start running your own shop, let's say you want to start your own shop, boy, you've got to get on the front end of it.
Right, right.
If you're going to get anywhere.
So you said we want to indicate, and I've never done this before. I mean, I've lined up threading tools to make sure I'm at 29.5 and on my compound and feeding perpendicular. But so you were going to just sweep this in? Yeah. See, what I do is I'll take a holder, you know, like this one, and I'll put it up in here and indicate it in. Well, when I indicate this one in, all of them are indicated in. You're good, right?
Because they're all indicated into this one, for example. And that way, when I go back and I use any tools, they're all square. Yep. So anytime I make one square or I want to do parting or anything like that, they're all square. The other thing is I put this on 45 degrees. The reason being, it's the most rigid position. 45 degrees is the most common angle you're going to find on any parts that you do.
Got it.
It allows you easy sight view of this cross slide, so you can turn the handle here and turn the handle here, of course, and you can cut 45s that way, and it's more rigid.
What do you do for your threading though? Single point?
Straight in.
Serious?
Oh yeah.
You don't worry about the 29.5?
No. See, you can, you know,
let's let the comments fury start now here, folks.
You can put it on 29 degrees under certain circumstances if that makes you feel good. I mean, you're taking a lot of steps in there. To give you an example, if you go out on a CNC, my particular CNC machine, it has 3 different cycles for threading, and one of them is it goes in 29 degrees or 29.5 degrees, just like John is alluding to here. It also goes in straight in, like I'm talking about, or it'll alternate. It'll go in one side, then the other side, and all you have to do in the program is select which type of threading you want to do.
Yeah, that's awesome.
If you're going to thread a real giant thread, you might want to put it on 29.5 degrees, but it's not really necessary when you're chasing a small thread, because you're not going that deep, particularly when you have inserts. The angle on both sides of the threading tool is correct.
Got it.
So you can just jump in there and cut it. It's, you know, up to, I would say, 13 threads per inch at least.
Course of that, you got to be more conscious.
You got to be more conscious about cutting both sides. I mean, in particular, you know, we were just talking about this Acme tool, and I just go straight in with it.
Now, when you talk about indicating, so this this new tool, if you put it in a new holder and push it up against the back of that holder,
you can, but sometimes these are made in China, and you know, anybody that's
but that's an Aloris.
Yeah, this is Aloris. This holder's made in China. Some of them are not made very well, as I'm sure a lot of people are aware of that. Some of them are. Some of them are made. I've got ones that are made in Japan. I got ones that are made in the States, which are Aloris, and and of course there's Dorian and a couple other ones. If you have them, you could indicate the back of your holder here and get them pretty straight. I mean, that one looks pretty straight. We could probably put the indicator up there and get it pretty good. I wouldn't doubt it's pretty good, but I don't trust the Chinese holders for that reason.
Sure.
They just
so just check everything.
Yeah, you know, if you double check everything, then you're not creating a problem that you don't see until you start cutting something and you go, well, what's the matter now? Rather than try to head off problems and proactive instead of reactive.
Yep.
So we're gonna set this up in here. I've got it in there flush, and I'll put an indicator on it. See what it looks like. And you'll notice on this particular machine, it does have a rapid on the cross slide.
Oh, that's cool.
And you'll see that it's out. It's out about 10 thousandths.
And that's not okay, right? I mean,
You know, that's generally what you would get in a CNC machine type environment. And like I say, this is not CNC, of course. There's no sense in, like I say, having problems that you wouldn't have otherwise. Oh, I'm moving it the wrong way. So if you got a machine with a rapid on like this, you get spoiled real fast.
yeah, that's nice.
It also introduces more wear into the machine than you would have in a normal lathe as far as the screw and the ways and all that, because you have a tendency to rapid it around a lot more than you would in a normal machine.
Wearing the screw or the gib or?
Both.
Yeah. Do you check those, maintain them?
Yeah, this one has a system where you can tighten it up. Actually, the other lathe has a better system than this machine because it's got 2 nuts in it.
Oh, you can adjust the preload?
Well, what you do is you push those 2 nuts apart.
Yeah.
And it tightens it up,
right.
You know, and
which just wears your screw down faster.
Well, it does, but you know, the whole thing is it keeps it tight.
Yeah.
And you know.
Do you really care about backlash in your cross?
Well, I'll tell you, we were just discussing threading, and it makes a difference in threading because you have to crank your handle backwards, and if you have a lot of backlash and you need to get out of there quick, you're not going to engage it. Reverse direction is easy. So we got that indicated in. I think I'll leave this here because we're going to throw a piece of aluminum up in there and get it indicated.
Thank you, sir.
So I use an indication system like this. I don't know how many people do.
I like that cold. You showed me that before, that piece of cold roll.
Yeah, you know, the reason they do that is if you company I work for, they had all their machines set up this way. You can indicate on a diameter like this, and then you can indicate on the face, and look how little moving around. You don't have to move the carriage back and forth. You don't have to stick magnets and adjust everything. You just turn it like this and indicate, and turn it like this and indicate the face. If you need a last word style indicator, you can put that in that holder and make it work the same way. And there's several style indicators that you can get that will function that way, but it's cheap. You know, we made this.
Right.
It's just got a set screw in the side. It's inexpensive. You can make them so you can put a line on there so you can set this down here and get your tool height right. You know, I suspect it evolved before they had magnetic bases, which are so widely available now. But it makes it so you can indicate really quickly without having to move the carriage up here and stick magnets to it and all that kind of carrying on. And if you do much indication, you realize really quickly that it's a real time consumer if you're trying to do real accurate work.
Same job.
So I can stick this up here and just sit it on there and get the indication really good if I want to. which we'll do with this, and we'll set the tool height here shortly. But anybody that's looking at a lathe, I tell them to get a 2060 myself. Just for, you know, you have to look around a little bit, just like you do for anything else. But the whole thing is, if you're going to use carbide tools, you want to be able to take advantage of them. You can't do that if you don't have enough horsepower, or the rigidity of the machine is limited. If you're buying inserts online, you know, and you were having the problem that we were talking about earlier with the people putting Chinese inserts, you don't want to open box. There's no reason to have a new inserts, all new inserts in the box and have it open. Well, there's no, people don't open boxes just to look at them. That's about 200,000. Okay, now this is what your chips should look similar to. They should be C's or 6s. If they're long and stringy, you don't want that, because those chips are really hard to control. They get wound around your leg, they get wound around the part, they cause all kinds of problems for you. They're dangerous.
I got that phone call from you.
They're dangerous, and you really don't want that. And you say, well, why do you want 6s and C's? Well, look how easy these chips are to handle. You can take them, you can put them in a chip hopper, you can haul them to the scrap yard, you can get greater density.
You're not kidding. Like, that actually matters to us now.
Yeah, that's exactly right. And chip control is what they call it. You want to control the chips and make them look like that. And you can even compress them a little bit more by increasing the feed even faster than what we have.
So feed harder to break the chips.
That's right. That's right. You don't want them strings. You got to feed faster, which means you got to have a rigid setup and you got to have some horsepower to make them break.
And feed faster is not RPMs; it's inches per rev.
That's right. Revolutions per minute is how fast you're feeding.
RPMs is this.
Yeah.
You mean the
the relationship between the feed and the revolutions.
Yeah.
Okay. Is what you're looking at. The more you feed, the more they want to break. The problem is, for a lot of people, is they don't have a machine with enough horsepower, they can't break the chip.
So what do?
You have to buy an insert that's designed for less horsepower.
Which means a smaller nose diameter, or positive?
Well, see, that's why do we have a radius on the insert? You know, you can get a real small radius, which this one has. Mm-hmm. What's it? It's less cutting pressure, it cuts a little bit freer, but it's harder to get a good finish with a smaller radius.
And it's going to, I assume it's a weaker insert because it has a
That's right,
smaller,
it's weaker.
More fragile
It's
tip.
a weaker insert. If you're going to feed real fast and you want a strong insert, you want a bigger radius. The bigger the radius, the stronger the insert. Right. You might as well go into, it's like this particular insert here. What size is it? Is this
432.
Yeah, okay, what does that mean?
It's a half-inch inscribed circle.
Yeah, so how deep can you go with it?
Half the IC.
Yeah, so you can go 250 deep without hurting it.
Radial depth of cut.
Yeah, that's right.
Crazy.
Yeah, and that's the rule of thumb, but that also depends on your machine. Does it have enough horsepower to pull that kind of chip?
Right.
And this particular insert's meant for aluminum, and they're not. Aluminum's pretty easy cutting.
Right.
If you're cutting some kind of 4140 or 4340 or some heat-treated steel or preheat treated, you're going to get a drag on the machine. And depending on the diameter, that's another factor too. We're cutting 6-inch diameter here. That's medium range, especially for a 20-inch lathe. That's not hard to pull for this machine. If you've got a 12-inch lathe and you're putting a 6-inch part in there, it's working it.
Right.
Yeah, it's taking some backbone for that.
And this is 2024, which you call the free machining aluminum?
It's one of the freest cutting aluminums you can get, which means it'll fracture really easy.
Okay. So we were doing 500 RPMs, 21 thou per revolution, and originally 100 thou depth of cut. So what we'll do when we chuck up the 61 pieces, take the same cut and try to compare those two.
Yeah, so we'll record what we're cutting now so you can see the difference between the cuts. And we'll push this a little bit and see what we can get out of it. But this is a pretty good, and like this, like we were talking about earlier, this is a positive insert, so you can't flip it over. You're going to only get 2 cutting edges out of this holder. If you want to get a real nice finish, you want to put a bigger radius on there to increase your, then you don't have to, you can feed faster and get a better finish. The bigger radius you have, the faster you can feed.
But there's an irony there, because that also means you can't take a little 5 thou cleanup pass, because with a bigger radius you need a bigger depth of cut to activate the chip breaker.
That's right.
That means I can't just sneak up on this final tolerance.
Well, that's just it. You might take this and make this your finished insert, and have another holder with a bigger radius to do all your roughing, and then come back.
Got it. Okay.
And normally on a CNC machine, which is what these are designed for, that's what you're doing.
Right. So let's, same material, same feeds and speeds, just let's go a little bit deeper cut.
This is not necessarily the kind of chip you want to get because it's curled up a little bit tight.
Too much.
Too much. It should be a C or a 6, which you can almost get a 6 out of that.
It's almost too much of a 6.
Yeah, it's a little bit too tight. Now, if you run coolant on it, it might probably loosen it up a little bit.
Really?
Yeah.
And we're not going to do that because of filming.
Yeah, that's right.
Okay.
And, but ideally, you want them to break up like this. This is not unacceptable. I would take those chips. I mean,
I can't believe how hot they were, though.
Oh yeah.
I mean,
but that's what the goal is here: is to transfer from your cut into the chips and not into the part.
Wow.
Because if you go over here and put your hand on the part, you can't. It's still cold.
So let's chuck up 6061 and see how it compares.
Okay.
Very familiar with that chip. Very familiar. So why?
Not feeding fast enough.
So you're gonna, what were you feeding?
21.
So you need to go faster than 21.
That's right.
Okay, so what are you gonna change it to?
You could change it up to 30.
Let's see what happens. So same RPM, same depth of cut. Let's go 30 thou per rev. So shorter, but not good enough. Much better.
Yeah, now you can see the difference between this one, and this one.
Oh, that's how much more.
Feeds, yeah, how the feed's stepping up.
Yeah, you can see the roughiness of the groove.
Yeah, now you can get if you get a bigger radius, you can get away with a bigger, much heavier feed and get a better finish.
Better finish, right. It's just like if you're using a sharp threading tool, you're going to cut threads.
Yeah, that's right.
Right.
That's right. And you're flattening the waves out.
So when we go deeper with this,
it'll chip better.
Better. Even the, so can we go 400 thou total, 200 radial with a 21 thou per rev and see what the chips looks like?
Yeah, let's go to the next step.
Okay.
200,000. See if it chips right at this feed or at right.
Same feed, which is what, 40 thou per rev?
So you see what they look like now. Let them cool off a little bit.
That them?
Yeah.
Wow, that's crazy.
So you know, if you
increasing the depth of cut totally changes that chip formation.
Right. Yeah, you have to. The inserts are designed for different depths of cut too. The chip breakers are affected by that.
Yeah.
And some inserts that you're going to buy will cut better at a deeper depth. But you can adjust that a little bit by changing the feed, just like we're doing right here. Sometimes it'll work and sometimes it won't. If it doesn't work, you need an insert designed for a lighter cut or a heavier cut, depending on what you're...
And going to a smaller inscribed circle, which is a smaller overall insert size, means you can take lighter cuts as a general rule?
Well, smaller inscribed circle, smaller insert, less cost.
Less cost, so don't buy all that carbide.
Yeah.
Okay.
If you're taking real deep cuts, you don't really want to use a giant insert.
Yeah, why would you?
The efficiency is going way down. That's just like this insert, let's see if I got one. Here it is. You see how big this is compared to my thumb. Mm-hmm. Okay, if you're only cutting that deep, you're throwing away all that cutting edge.
Right, why buy all that? Right.
And then you can get, of course that's a triangular, you can get a W, and of course the W's, you know, they got 6 sides on them. Mm-hmm. Well, this one here, we got this because we were only cutting as deep as this side is. And the closer you get to the maximum depth, the more efficiency you're getting out of the insert.
Sure, right. Well, you were mentioning no DRO on this lathe. Why is that?
Mainly because a couple of the parts we're doing in here, it limits the capacity of the machine, and we're pushing it right up to the limit.
On travel?
That's right.
Interesting.
Yeah.
Huh. So you need a bigger lathe?
Well, we could use a bigger lathe. I'm too cheap to buy one. I really must know the truth. I mean, the tailstock, for example, won't hang out far enough. So if we put a digital readout here, then it's going to be too far, and it's just enough the way it is, and that's it. Now, we can put the digital readout here, but then I've got some big parts I'm turning on here. Mm-hmm. It interferes with that, so I just give up on the idea for now anyway. But anyway, you want to go ahead and take a 200 per thousand per side on this thing, 400 thousandths total depth on this cut.
That's what we just did.
I think that one was 300.
Oh, okay, sorry, Julie. Okay, so that was 300, so now we're going to do 400,000. We'll keep rolling. And maybe leave me some of this one to do a slow-mo, okay?
Now you see it's about to the center of the insert there on the depth of cut. So this is the maximum depth of cut for this insert. You might be able to push a little bit more on the feed, but we'll go with it. Making a chip like that, you can see it's a little bit of a spiral. The only way you can
oh yeah, the spiral.
Yeah.
So we don't like that.
Yeah, we want to lessen that. Well, the way to lessen that is to increase the feed or increase the depth of cut.
Okay.
Now, a lot of times you don't have the luxury of increasing the depth of cut.
Because of horsepower.
Because of horsepower, so the only way to defeat that is to increase the feed. I mean, you can get along with little spirals like that. It's the great big long ones you don't want to get. But this is an indication it's not feeding fast enough.
Okay.
So we can feed it faster. We'll go ahead and we know what we can do. Let's try taking a larger depth of cut. We'll go 200,000 this time.
So you were just saying,
if you look at this insert, since we've used it some, you can see where some of the aluminum is sticking to the insert there. And you know, if you want to minimize that, you can run coolant on it, you can put oil on it. My preference is coolant because it doesn't make smoke. I have to quantify that a little bit because I know some guys don't use their coolant enough to keep it fresh.
Got it.
You know, and to do that, you have to run it periodically, no matter what.
You can do the pond aerator that can help just keep
that's the point. It needs air.
Right. Well, and folks, video link here to the series we just did with QualiChem, where we talk about why does coolant get stinky and having anaerobic bacteria that starts to grow because there's an oxygen layer, a layer at the top that prevents oxygen through it. So there are solutions to it, but coolant is great, and it's going to help your tool last. Now that we've had some chip weld build up on that, are you okay with that, or would you say no?
I would rather not have that because that could cause it to fail. But you know,
So if you're working on a critical part, you'd rotate or swap the insert?
No.
No.
No. If I'm roughing like I am now, I'm keeping going, but I'm running coolant on it.
Yeah. Okay.
You know, and we're not running coolant on it, and that would prevent that from happening. Basically what it is, it's just melting some aluminum right there at the cut point.
Yep, and that's crazy because that's a polished and ground insert, which it means if it's not polished or ground, it's going to happen. That's going to happen even sooner.
That's right.
Yeah,
it'll get worse. I mean, we could use standard inserts on this. We might do that so you can see what the difference is. I can just throw up a standard insert I've got here, and you can see why you need this type of insert for cutting aluminum.
Cool. So folks, take a look at the differences we've got here. The 2 cuts from 2024, 3 from 6061, and the 3 from 7075. You want to talk about what you like and don't like, and like even for me, the last cut that we did on the 6061, you know, that to me, I see tearing there.
Yeah, well, you're not worried about that because you're roughing.
You don't care?
No, I don't care about that. But, you know, if you want to cut a little smoother, get a bigger radius on the insert.
Or use coolant
on it, you know. And then I know, like I said earlier, some people don't want to use coolant because it goes bad on them, but you've already done some video on that to help them out with that. It's just a matter of air more than anything else. Depends on how regular you use your lathe and use the coolant in it, which you should use it a lot. It saves your tools.
What's your favorite insert? Well, you know, in terms of the C or 6 in that pile there.
Well, probably these right here on the 61s are the closest to what you really want to get. Now,
you're calling that a C?
Yeah, and this one here is pretty close to it too. It's deformed a little bit, but that's all right. If you have a different radius size on the point of the insert, it's going to be a little different than that. It forms differently, depending on how fast. I mean, you can feed real fast and get a nice finish with a bigger radius. A smaller radius, if you want to get real sharp corners, sometimes you can't get around it. And you don't want chips like
I was going to say, that's the only one that's totally unacceptable there, right?
You know, even if it breaks into short pieces like this is not terrible if that's all you can get out of it. And let's say you don't have the horsepower or you're not cutting that deep. That one's acceptable. You just don't want them long stringy things getting wrapped around your chuck, your part, or you.
Yeah, sure.
So you don't want it to have that. You want it to break up like this, and then you can go and shovel your chips out and put them in a 5-gallon bucket and get some density. And most manufacturing facilities, that's what they want. They want to be able to control that.
Right.
And automate it, really. Conveyors and all that stuff handle that way better than all that stringy crap.
Yeah.
Not only that, it's much safer for their people that are working there.
Even in a CNC lathe, I mean, those big strings can get caught up in a turret and wreak havoc.
Oh yeah, you know, and get wound around the part and make a real mess. They call them bird's nests, is what typical.
I'm familiar with the term.
Yeah. Now you may want to run a little slower than If you run slower RPM, what we were running is 500 RPM, which is the maximum I can run with a 16-inch 4-jaw on this machine. That's 800 surface foot, so we're on the low end for aluminum.
Crazy with carbide, yeah.
Yeah, that's right. With carbide cutting tools, that's the low end. So to really get more efficiency, you have to jump up into the next level. Now, we're using a 4-jaw chuck, and if you're really going to hog like we're doing here, you really want to hold it in a 4-jaw. Unless you've got board jaws and a finished part to get a nice clamp on it, you want to hold that thing tight if you're really hogging on it. That's true of steel, aluminum, or anything.
Yep.
Some of the jaws that we have on some of these Chinese chucks, like this one here, this is a Chinese one, you see these are smooth, and I'm not a big fan of that. I like ones with teeth on to dig in.
Yeah.
And that enables you to clamp something way out here on the end so you can salvage as much material as possible. These are smooth, and you can get a lot of pressure on this, but it's not quite as good as the serrated teeth in my opinion.
And if you had serrated and you didn't want to mar it, you just put some shim in?
Yeah, you just put some copper pieces like that in there. You know, or some people wrap them around here to hold them on there. I use these, and I have we put this up here like this. So when you're indicating your part and you put these on here, if you drop one of them, it just fits right here.
You don't like fishing?
Take it out of the chip pan.
Yeah.
But some people wrap them. You could say I'm cheap, but this is the way I was taught to do it. Now you can't put smaller pieces in there, and it does make it easier to indicate than bigger pieces. But this type of jaw, you want to clamp it very securely if you're going to hog. Now you can, like I say, you can clamp it if you got the serrated teeth, and even on this one, I clamp it out here on this one tooth.
On one tooth?
Yeah.
No kidding.
That's right.
Wow.
You can hog pretty good. I mean, you showed those bigger pieces there earlier. I'm only holding them on one tooth right here when I flip the jaws around.
But it's important to note you're using the T-slots with backing spacers.
That's right.
Right.
So, yeah, that's the other thing. If you're pushing on it real hard, you better have something back here for it to go on, because sometimes it'll push it back in the chuck.
Right. Right.
And of course, you have to quantify all this. This is 10 horsepower. Some of them are 15, some are 20. Some of the machines that I've run in the past are 40 horsepower. So you can really push that machine really hard, and you have to prepare for that, and that means the machine has to be rigid, your setup has to be good, and then you have to consider, is the part thin?
Right, deforming it.
Fragile. What kind of part is it,
right.
and how are you working on it, whether it would withstand that kind of cutting pressure?
Well, we caught a lot of heat for the servo video, the servo housing, and you phone called me and said, John, you're collapsing that part with your forejaw. We blew our tolerance on the back side of that board because we were clamping down too hard on it.
Yeah, that's right. See, and if you have to gently hold it, by that I mean you're not getting a big pipe on here and yanking on it. You have to think about that. Now that the servo piece that you're talking about, if you clamp a piece in here with 4 holes in it, and let's say that disc is solid and it just has those 4 holes in it, you can clamp this disc as tight as you want.
Right.
Skim it off.
Yeah, face it. Right.
So folks, thank you for watching. Thank you to Paul for coming out and teaching us something. Talk about a win-win. Paul actually substitute teaches at one of the local machine schools, and so he's going to take these pieces of material over and work with the kids on understanding that aluminum just isn't aluminum. There's different machines, there's different tools, there's different feeds and speeds. So thank you to Alro. I'm happy that the material gets to keep paying it forward, and we'll take it from there. But thanks for watching, folks.
Yeah.
See you soon.